Welcome to the lesson on digital twins. Upon completion of this lesson, learners will be able to define digital twins and differentiate between their various types, discuss the key components that make up a digital twin system, explain the process of designing a digital twin specifically for an EV manufacturing facility, and analyze case studies demonstrating the practical implementation of digital twins in EV manufacturing environments. Digital twins are revolutionizing modern industrial operations. They are virtual replicas of physical objects, processes, or systems that use real-time data and simulation to accurately mirror the behavior of their real-world counterparts. This technology enables comprehensive monitoring, analysis, and optimization of the physical asset or process, allowing organizations to improve performance, predict maintenance needs, and make data-driven decisions. Some of the key types of digital twins discussed in this lesson are component twins, asset twins, process twins, system twins, and organization twins. Digital twins operate at different levels of complexity from components to complete assets. Component twins model individual parts or components, such as a single engine component or electronic components, and focus primarily on basic performance and wear monitoring. Moving up in scale, asset twins represent complete standalone machines or products, like entire wind turbines or vehicles, allowing for comprehensive monitoring of overall performance and maintenance needs across the integrated system. Beyond individual assets, more sophisticated digital twins model entire operations and systems. Process twins simulate operational workflows and procedures, such as manufacturing production lines or supply chains, enabling organizations to optimize output efficiency and identify bottlenecks. System twins model complex systems with multiple interacting assets, like entire power plants or smart factories, allowing for management of system-wide performance and integration across all components and processes. Organization twins represent the highest level of digital twin technology. These models simulate entire enterprises or facilities, such as complete factory networks or city infrastructure systems. By providing a holistic view of operations and interactions, organization twins enable high-level decision-making and strategic planning across the entire enterprise ecosystem. Now let us look at some of the important components of a typical digital twin system. At its foundation is the physical object being monitored, complemented by sensors and data collection methods that gather essential information. This data is stored in dedicated storage systems, which feed into the digital model, the virtual copy of the physical asset. Analysis tools consisting of smart programs process this data to generate insights, while the user interface provides the means for people to interact with and control the digital twin system. Designing a digital twin for an electric vehicle manufacturing plant involves several critical steps either in sequence or simultaneously. These include mapping and documentation, sensor installation, data system setup, 3D modeling, and integration. We will discuss more about these steps in the upcoming slides. The first two phases of creating a digital twin for an EV plant focus on documentation and sensor deployment. Initial mapping requires developing detailed floor plans of the facility, creating complete lists of all machines and equipment, documenting every manufacturing process, and identifying the key points that need monitoring. Once the mapping is complete, sensors are installed strategically throughout the facility. These include sensors on critical equipment like battery and motor assembly machines, surveillance cameras for visual monitoring, and specialized sensors that track temperature, energy consumption, production rates, and quality metrics. The next two phases focus on data infrastructure and virtual modeling. The data system setup involves installing robust computer networks throughout the facility, implementing data storage systems to handle the information flow, setting up processing centers to manage the data, and establishing security measures to protect sensitive information. For the 3D modeling phase, engineers create an accurate virtual copy of the entire facility, including detailed digital versions of all production lines, precise machine models, and worker stations. This virtual representation needs to match the physical facility exactly to ensure accurate monitoring and analysis. The final integration phase brings all components together into a functioning digital twin system. This involves connecting all installed sensors to the digital model, establishing reliable real-time data feeds from the production floor, and ensuring seamless communication between all systems. Engineers must thoroughly test every connection and data flow to verify that information from the physical plant accurately updates the virtual model in real time. This testing phase is important to confirm that the digital twin accurately reflects actual plant operations before it goes fully operational. Once the digital twin is operational, several ongoing processes ensure its effectiveness and value. The system requires constant data monitoring, regular model updates, continuous improvement identification, staff training, and systematic maintenance and upgrades. These efforts deliver significant benefits to the facility. Operators can observe entire facility operations in real time, predict and prevent potential issues before they occur, safely test modifications in the virtual environment before implementing them physically, improve overall operational efficiency, and minimize production downtime. Let us examine a practical scenario where digital twin implementation delivers measurable benefits in manufacturing. When a robot welding station shows decreased speed in an assembly line, the digital twin enables real-time monitoring of performance metrics, analysis of movement patterns, and simulation of alternative configurations. Based on typical industry implementations, this approach to production line optimization can yield significant results. In this hypothetical example, a 15% increase in throughput, a 20% reduction in energy consumption, and a noticeable decrease in quality issues. In another hypothetical example demonstrating digital twin capabilities, let's look at paint quality control in an EV paint shop. When monitoring paint consistency, the digital twin system conducts real-time paint thickness measurements, tracks environmental conditions, and performs detailed defect pattern analysis. This continuous monitoring and analysis approach could potentially lead to significant improvements: a 40% reduction in defects, a considerable decrease in material waste, and notably higher customer satisfaction ratings. These outcomes illustrate how digital twin technology can transform traditional quality control processes. In summary, digital twins create virtual replicas of physical systems, from components to entire facilities, enabling real-time monitoring and optimization. Implementation follows 5 key phases: mapping, sensor deployment, data setup, 3D modeling, and system integration. The technology enables predictive maintenance, virtual testing, and real-time process optimization. In automotive manufacturing, digital twins can improve production efficiency and quality across multiple processes. Success requires ongoing system maintenance, staff training, and continuous improvement. Thank you.